So hello everybody. I should switch now again to English. I think it would not be problem for you. But my name is Mehrnaz Anvari. I am from Fraunhofer SCAI. So yeah, there is a lots of shadow here, but I hope that you could see now everything. But yeah, I am from Fraunhofer SCAI. If your question is that where is it, I should say that it is in St. Augustine. And today I will talk about what we are doing in my team, which is called Network Evaluation Technologies. And in my team, we are planning and doing the simulation of the energy networks. And for this purpose, we are using our software, means that I will also introduce our software today to you. So fortunately, this one, it doesn't work, so I should use here. In the previous talk, we have already heard about the plan or the strategy in the Germany and the Europe for going to the zero emissions in the future. And here I would like also, as a very short introduction, to remind you the sixth assessment of the IPCC, which was published in the mid of 2023. And maybe you have already seen this very famous statistical analysis about the temperature and how is the situation at this moment. And unfortunately, the statistics shows that we are not in the good path. And if you look at the temperature, the increase of the temperature between 2011 to 2020, the temperature was 1.1 degrees Celsius warmer than 1850 to 1900. And if we don't do any fast action, unfortunately, we would be in one of these worst scenarios. And I hope it will not happen. But it means that we need the fast action in the different sectors and to go to the net zero emissions. And the energy network is one of the purpose. Because of that, we need the energy transition. And today I want to talk about the goal of my team for this supporting of the energy transition. So just again, as a short reminder, I thought that this plot, it would be helpful to see together that where we are now exactly in the energy sector, how much we were successful in the previous year to reduce the CO2 emissions in the energy sector, and still where we should go till 2030, and then in 2045 till 2050 completely to the zero emissions. Good. So, as I mentioned also at the beginning of my talk, we are also supporting this energy transition. And for this purpose, we are also developing our own software, which is called MEANS. And MEANS is the abbreviation for the Multiphysical Network Simulator. So my talk, it would be a little bit different from the previous talk. I really talk about the infrastructures, the network infrastructure, and how we should plan this network infrastructure in the future, and then also the simulation and the optimization also of this network. So a little or a brief introduction about MEANS. I should say that we design MEANS that we could look at the different energy sectors. This could be the gas, it could be heat or water or electricity, but because of the projects that we are now focusing on it in my team, we are working a lot on gas networks and also in electricity. And today I will show you some examples in both of these fields. So when I am talking about the MEANS gas, it includes natural gas, hydrogen, CO2, and we have the stationary and non-stationary solution for this calculation, simulations. And also we are looking at the gas phase and also liquid phase for this fluid dynamic. And I will tell you later better that why all of these things are important, or we are looking at it. And when I am talking about the electricity, we are looking at the DC, AC, and also the economical optimized power flow that maybe for some of you this term are familiar, but if not, we could discuss later if you would like to know about the details. Good. Now I could go to the topics that we are working in my team. And if you are interested in any of these topics, yeah, you could contact me. We could always discuss. And if you would like, we could also collaborate together. So the first topic is the hydrogen network. As I told you, with the gas, means gas, we could do the simulation and the planning of the hydrogen network. And we are, of course, very interested in the green hydrogen. And what we are doing, we are planning and simulate a German hydrogen network and also a European hydrogen network. And then we are optimize this network for 23 bis till 2045 across diverse scenarios. And with the diverse scenarios, I mean that how much hydrogen we need for the, for example, industry, for the households, or also the combination of all of them. So we have the BMBF project, Trans-Height system analysis, that they have also booths here in the Halle 5, but I forgot the number of the booths. But if you are interested about this topic, you could go there, and my colleagues are there, and they could give you more information. The other topic that today I will talk about it more also, it is a CO2 network, because as you know, there are some parts, some industry that they could not avoid the emissions. And the idea is that, okay, we could capture this CO2 emissions from there, and then we should transfer to the some other industry that they really need CO2, or we could also store them in the storage. So again, we are planning and simulate both a German and the European network, and also optimize network parameters for this CO2 transport, specifically for the liquid phase. And I will explain you later why. And then if I forgot, then remind me. And then we have also recently a project from a European project. It's called Eastern Lights. If you are, and the idea behind of it is that to look at the storage in the east of Germany, that we could in the future bring these CO2 emissions to this storage. And at the end, we are also interested in the coupling between the different networks, because we are looking at the different energy sectors, and then it is interested to know that what will happen or how we could simulate or have the still energy balance when we are talking about the coupled system, for example, gas electricity system. And then again, optimize this coupled network to boost the renewable energy share in our energy sector. And at the end, when we are talking about the coupled network, and we would like to make a stronger the couple between our energy network or energy sectors, then we should be careful about the resilience of this network, because we could have some time that we don't have any renewable energy such as wind or solar, or we could have kind of very extreme weather events that they could really destroy the infrastructures on your land. And then it means you have kind of a spread of the failures inter and intra your different sectors in the system. So what recently we are doing, we are also trying to use the artificial intelligence method to find the vulnerabilities in the network, and then in the next step we could increase the resilience of the network. But of course that today I could not speak about all of them, and I will focus just in the CO2 network and also sector coupling, and I will show you 2 examples, then you could have better idea that what we are doing exactly in my team. So let me start with CO2 transport network. Here is the idea about the CO2 network in Germany till 2045. We got this data from our colleagues from Fraunhofer SCAI, and you could see that, for example, where is the Quelle von, source for the CO2, and where is, for example, sink for CO2. We have also with these yellow squares, we have shown the neighbors neighbors of the Germany, that we could have the transport, export, and import of the CO2 between Germany and the other countries. And then we have the hubs that it has been shown with the red triangles, that all the CO2 emissions would be collected and go through these hubs, and after that to the storages. So as I talk about our means a lot, and I don't like that it would be just a name for you, I thought that the short video, it would be nice that you could get some idea about our software. Here is the GUI of our software that you could see, and we should import definitely the information about the topology of this network and also scenarios. And with the topology, you could, for example, define where is the neighbors here, in your neighbors of the Germany for the import and export, where is the, for example, hubs in the system. You could define all of these things, and then also import the scenarios in means. So now I give you some idea that how does it look like means. So after having that, now we should know also the scenarios. For example, how much CO2 emissions we have in each of the sources, or how much we should transport in this network. And for 2045, we have the different scenarios based off the import, export, carbon capture and utilization, and also, for example, waste incineration for the carbon CO2 emissions. And we are doing all of these simulations for this network, but I could not show all today. But I thought that it is not a bad idea that I could show the simulations for the max transport. Maybe you could guess now from the name that when I am telling max transport, it means the maximum transport we could have in this network. And if it would be successful network that we could have the maximum transport, then it doesn't matter if you have a less CO2 transport in this network later, because then we have completely the balance in this network. So again, for each of these scenario, we could have all of these details that we should also define them for our simulations, for our software means that, for example, how much volume for the CO2 we have for each sources in the hubs, in the, for example, the neighbors. And then we do the simulations. And of course, when we are talking about the gas network, maybe you could guess that something that it is important for us to know that how is the temperature or the pressure in this system. That here it is the results for the pressure that I have shown here. And for the details of the calculation, I should say that here the results, it's related for the stationary simulations. We have done this simulation for the liquid phase, and the roughness of our pipelines is 0.036, and we always change the diameter from 50 to 100 centimeter, but this specific result is for diameter equal to 70 centimeters, and temperature soil is 10 degrees Celsius here. So now I could, as I promised you, I could mention briefly why a liquid phase it is important for us. Although that transport CO2 in liquid phase could be expensive for the gas operator, because they need really the new infrastructure, the new pipelines in the network. They could not use the existing natural gas pipeline for the CO2 transport, but it is beneficial for them because in the same time they could transport the huge value of the CO2. So still they are interested to look at the liquid phase. But some other thing that is important here is that they should become sure that during this transport, the phase will not be changed. If we are interested in the liquid phase, always the CO2 is in the liquid phase and not jump to the gas phase, or we have kind of combination of gas and liquid, because then it would be really dangerous for the network and for the pipelines. And it's what we are doing also with our software is try to show this phase diagram and check for our network system that it is always in the safe situation. And here in this phase diagram, you could see that always all the pipelines are in the liquid phase and there is no any problem. If there would be any problem, then you should go back, check your parameters, change your parameters, and then to find again based on which parameters you are still in the liquid phase. Good. So now, if you look at, I don't know, maybe you have already seen that the highest pressure in this simulation is 516 bar. Then you could ask me, it is crazy why we have this this huge pressure here. And I would tell you that you are right. Because of that, in the next step, we should add pumps in the system to control also the pressure in the system. But in the first step, already we let the simulation or the network would be free and let it that the pressure goes beyond 200 bar. But then we look at the network and find the place in the network that we have very huge temperature pressure, sorry, that you could see it is in the southwest. And then what we are doing, then we are looking at this segment individually, and then we should also become sure that we don't have any very large loop here. We have just a small loop. It is okay for the next part of the simulation. But now we fix the pressure here to 200 bar and not let it to be any more 563 bar. And then we do again our simulation and look at the flow and the pressure. And when it became 0, that it is here, and became then negative, then we should add a pump before that this pressure became negative. So then we add pump here and then repeat our simulation. And then we did it till the end. I mean, we divided the network to the different segment, and every time we do these simulations, and till the end that we find that how many pumps we need for this network. And here is also some results that maybe it would be interesting for you and give you some idea about the cost for the CO2 transport in Germany. So as I told you, we are doing for the different diameters for pipelines. Here is the result for 500, 700, and 900 millimeters. And for the 700, we need 20 pumps for this network. If you go to the less or a smaller diameter, you need more pumps. And if you go to the larger diameter, you need less pumps. But something that is important, it is the cost of this pipelines. You could see that when we have the larger diameter, it is more expensive. And at the end, if you think that here we have the 5,000 kilometer pipelines, it means we need something between 12.5 to 17.5 billion euro for this network. And if you look at the report of the Verein Deutsche Cement, that is Association of German for Cement, they also said that for 2045, they need around 4,800 pipelines for the CO2 network, and it costs for them around 40 billion euro. But the point here is that it is just for the pipelines. You should also think about the cost of the number of pumps you need for this network, and then you should optimize your network really based off the really how big should be this network transport and how many pumps you need, and then you could decide that which diameter it is more beneficial for you. But to close this section as a take-home message, just I would like to tell you that after lots of simulation, looking at lots of scenarios for the CO2 network in Germany, we understood that if we want to have the economical CO2 network in Germany, we need the plan and the pipelines to the neighbors in the west. For example, if we have these pipelines and the export to the Belgium, then we could say we could a little bit reveal this CO2 network in Germany, and then you could also use the pipelines with the smaller diameters. Good. If you are interested in this topic and you would like to know more about everything that we have done, I would like to invite you for our workshop in Bonn, which is in 12th of March. And yeah, the barcode is here. You could just scan it now and register and participate in our workshop in March. So now the last topic for today is the sector coupling, and I want to show also one example for the integrated electricity gas network and how we do this simulation in MEAS. So here I thought for the visualization reason, it is easy if I show you or I start with very small network. Here I have the gas network with 47 nodes and 23 of them are consumers and we have 46 pipelines. So in the other side, we have the electricity network that we have 173 buses here, 7 generators here need gas to work. And then the transmission lines have they are 230 and 69 kilowatt. So now in the next step, we combine both of this network. And it is important now to simulate the coupling between them. What I mean with coupling here, we need coupling between the electricity network and gas because I told you that 7 of these generators need gas. It could be the natural gas or it could be also hydrogen. Also, we have 2 compressors in our gas network that I forgot to show or mention it here, that one of them is here, one of them is there, and then they need also electricity to work. So now we should also model and have this coupling for the energy consumption of the compressors. And at the end, what we are interested to answer is that, okay, I have the load profile for every hour for 3 days for the electricity. And now I should answer this question that how much energy I need from the gas network to electricity network that these 7 generators could work. And now it is the result for the energy I need for each of these generators for every hour. So it was very a small example, but something that now we are interested in it is that we have the core hydrogen network in Germany, which has been shown here with the red color. And now I have also the extra high voltage of the electricity network in Germany because I want to have the connection to the wind part and the solar part. And then now I need for my electrolyzer for the green hydrogen, this energy from electricity. The resolution is bad here, but I could guide you to find the electrolyzer. They are the green circle. We have here, for example, we have something here, and it is some also optimization process behind of this process, how to optimize the location of the electrolyzers in this system that we could be more beneficial for our network. And so I should add also in the next step the model for electrolyzers in this network, and then answer, and then again look at to this load profile and answer to my questions that how many energy we need, for example, every hour for our gas network or also for the electricity. But now we are waiting for the scenarios from our colleagues that we could start also this simulation. So if you are interested, then you could follow us and get more information or results from this simulation. So now I think I am finished with my talk, and I am waiting for your feedback, your suggestions, and your questions. But if now you don't have or you need more time, you could find us also in booth 170 in hall 4, and I am there. And you could also work with our software if you are interested there, and I could show more about our software and our simulations there. Yeah. Yes.
looks like it reduce the diameters and also reduce the cost.
Yeah. Again.
Smaller.
As I told you, one of our answer is that as I shown, our simulations show if we have the more pipelines or the plan for the west of Germany, then we could really reveal and the load would be less for the German network. But still, we should also think about the pumps, because if you want to reduce, then you should need more pumps, and then you should kind of optimize, doing some optimization between the number of the pumps you need and the diameter of your pipelines, and then at the end decide that which one is in the long time, in the short time, it's beneficial for the energy operator. Yeah. It is a little bit challenging. I mean, I could not have now very concrete answer to your question. So then, yeah.
You mentioned at the beginning that the possibility to transport CO2 in gas state in existing infrastructure. Do you think about making an assessment? What could be the balance between reusing something existing and adding infrastructure as you designed it? Or is it not very?
Yeah, I mean, it is also something political but from my scientific point of view, if I want to answer this, we think about it because we thought that, okay, we could have a part of the network that they are in the gas phase and the other part in the liquid phase. Because if you use it, if you want to transport in the gas phase, you could still use the existing pipelines, and it is also beneficial. Then from the modeling point of view with simulation, there was no any restriction. Although we need, for example, some valve controls or the compressor to become sure that everything is in the correct situation, or not go to the dangerous phase, but it is possible. I mean, at least from the simulation and the scientific point of view. Yes.
How did you consider the mass flow in the pipelines? Because at the beginning, there won't be not so many carbon capture units in the south. The first one starts, but then in 20, 30 years, much more companies will join it. So at the beginning, it's only a small flow, but nevertheless, you need to liquefy it.
I think that I answered this question with this maximum transport scenario. Because the idea was that to answer this question, this scenario, it was for 2045. So then we are also maybe now at this moment, we don't need this network that I show you here. This is for 2045. When we have more companies, more parts of Germany, they want to join this carbon capture, and then because of that, I told you also today that if it would be successful to have a network for the maximum transport, then we are ready for the future when they want to join for this process. Yeah.
If you look at the overall budget, is there any requirement for approach?
I didn't get the first part of it.
Any requirement for storage?
Yes.
Or if there's maintenance in the advanced model.
Yeah, your question is that we need also in our model to include the storage. Yeah.
Exactly.
Yeah. Now I could look at it as the sink in the very first step, and the easy answer that we have different nodes. One is source, one is sink. So this thing could be a storage, or it could be some industrial part of Germany that they need CO2. But then it is something that is important, and I mentioned about our software that we are also looking at the non-stationary or transient model, that then for the safety, for example, during the time we should have this transport of the CO2 to the storage. And then it should be maybe some restriction. And then you should model also this one, because then they said now we could not set any more CO2. And then we are doing, because of that, also a transient simulation to answer also this kind of question, that when given the time, it should change this value of the Do I have still time?
No, we are
Sorry, but I told you where we are. You could come there. I would be happy to discuss with you.